Standard C++ has no support for graphics and only works with text in the form of console applications. Graphics operations involve direct access to the pixels displayed on screen in order to draw shapes. Various graphics libraries exist to support these operations in C++, such as Direct3D for Windows and OpenGL for cross-platform applications. Both of these libraries are quite complicated for beginners, so to get you started, we'll be using a free library based on OpenGL called Allegro. Allegro can be installed on many platforms including Windows, Mac, Linux, iOS, and Android. It's a third-party library, meaning it's not a part of Visual Studio. It can be found at allegro.cc. Installation on Windows requires copying the contents of 3 folders to various locations on your system. The locations are as follows. The contents of bin go to Windows/System32 and Windows/syswow64. The contents of lib go to Visual Studio/VC/lib. And the contents of include go to Visual Studio/VC/include. As an alternative method of installation, you can copy these files anywhere and add their location to the Visual Studio project path. This can be done by going to Configuration Properties and VC++ directories. You can also use the NuGet package manager in Visual Studio to add Allegro support to each project. To create a project using Allegro, you need to define the library you're using by following these steps. First, create a new Win32 project. Don't pick the console version this time. Select Empty Project under Application Settings. Next, in the source file, you need to include allegro5/allegro.h. Then you need to go to Properties, Linker, Input, and under Additional Dependencies, add allegro-5.0.10-monolith-md-debug.lib. Keep in mind that Visual Studio has separate project settings for debug and release modes. To use release mode, add allegro-5.0.10-monolith-md.lib. We're using Allegro 5.0.10 in these examples, so if you're using a different version of Allegro 5, the file names might differ. Also, older versions of Allegro are incompatible with Allegro 5. Moving on, in Linker System, set the subsystem to Not Set if you want to see the text console. This is very useful for displaying system information or debug messages. If you need more information, you can look at the Allegro 5 manual at alleg.sourceforge.net/a5docs/5.0.10. To get started using Allegro in your program, you'll first need to include the necessary libraries and create some global variables. Allegro.h is the main header file for all Allegro programs. Some Allegro functions need extra headers to be included. For example, drawing graphic primitives such as a line is supported in a separate header file. Allegro defines some new data types such as Allegro display using a C++ method called structures. Additionally, it also uses pointers, represented as an asterisk after the data type. Both of these things will be discussed in later modules, so no need to worry about them right now. In addition to the main function, Allegro Sample 1 includes a series of other functions to modularize the program. Init Allegro and End Allegro are used to start and end the Allegro program. Put pixel and draw line are used for drawing dots and lines. We can use the wait for key function to receive user input. Our functions in this program use Allegro functions, which are prefaced with AL underscore. For example, putPixel receives 5 numbers which represent the coordinates of the particular pixel on the screen and the red, green, and blue components of the color. It uses the AL underscore map underscore RGB Allegro function to create a color code, and then uses that code and the coordinates to call AL underscore put underscore pixel to draw the pixel. Keep in mind that a function which returns a value can be used to represent that value itself. We can use some variable c to temporarily hold the value returned by ALMapRGB and then provide that to ALPutPixel. Alternatively, we can just directly use ALMapRGB as a parameter in ALPutPixel to make the program shorter. Another thing to think about is that in most graphics libraries, any color can be defined using the 3 components of RGB color values. Most computer systems allow 1 byte of data per component, so the RGB values range from 0 to 255. The location of a pixel is defined in a 2-dimensional coordinate system with x and y axes. Again, in most graphics systems, the top left of the screen is the origin, which means the positive directions are down and right. This trips a lot of people up, since it's a bit unintuitive to think that down on the screen is the positive y direction. Moving on, the initialization of Allegro in this sample code is done within a new function called init Allegro. It calls AL underscore init to start using Allegro, and then proceeds to set up different parts of Allegro, starting with the creation of the display. We also have End Allegro, which is used to clean up the processes Allegro uses at the end of the program. If we take a look at the main function, we can see the general structure of the code. Remember from before how we were saying we wanted to separate out functions and code? Well, this is why. Instead of having all of Allegro's functions in this one file in addition to our own ones, everything is kept apart. Main now just shows the basic form our program takes, which is as it should be. First, it initializes an Allegro window using SW and SH as the dimensions. Next, it draws 2 pixels of different colors to 2 locations on the screen. This information is stored in what's called a secondary buffer in computer RAM. This is because writing directly to graphics card memory is really slow, so most graphics programs, including Allegro, do things this way. Once all the drawing for a single frame is done, it'll be sent to the graphics card to be displayed on the screen. This is done using AL underscore flip underscore display. We then wait for user input. Finally, End Allegro cleans up and terminates the library. But how do we draw something more complicated than just a couple of dots? We can easily draw a line using a loop. We can also draw a rectangle by using a nested loop or double loop. The double loop is just a loop within a loop. It's a very common process for accessing pixels in an image or an area of the screen. The outer loop controls the x dimension, and the inner loop controls the y dimension. In this case, the x-axis is controlled by the I variable of the outer for loop and goes from 100 to 120. The y-axis is controlled by the j variable of the inner for loop, and that goes from 150 to 170. PutPixel uses the ALPutPixel Allegro function, which is a slow operation as it accesses graphics card memory directly. Using it is not recommended for large areas as it slows down the program. Later, we can see how to improve the graphics operation using bitmaps and memory buffers. Allegro has functions and data types for accessing the keyboard too. We've created a helper function that reads information from the keyboard and waits for a specific key. This function causes the program to pause and do nothing while it waits. That's not the best way to do things, though. Halting the entire program until the user presses a key is not always practical because sometimes you want things to happen in the meantime. For instance, in a game, you want to do things such as move characters around or render this frame while waiting for user input. That said, reading from the keyboard in this fashion still allows us to interact with the user, which is what we want. In this example, we move the player character in a game. Allegro has functions to deal with images as well. In order to use them, we first have to include the appropriate library, allegro_image.h. As with other aspects of an Allegro program, there is a structure to contain all the image information, allegro_bitmap. To use a bitmap, we create a new Allegro bitmap and use the asterisk to specify that it's a pointer. Again, we'll cover pointers and structures in later tutorials. We give the pointer the value returned by al_load_bitmap, which takes the file name of the image we want to use. Then we draw the bitmap using al_draw_bitmap, providing it with the pointer as well as the x and y coordinates. In the previous tutorial, we learned how to read from the keyboard and wait for a key to be pressed. The wait for key function we saw in Allegro Sample 1 is helpful if we want to pause the program and do nothing until the user presses a particular key. However, in most programs, the user is allowed to press multiple keys for different purposes, and the program might need to do other things while awaiting input from the user. In this tutorial, we'll take the first steps towards making a simple game by moving a player character using the keyboard. We can adapt the code in wait for key to suit this purpose. First, we create a variable to contain the state of the keyboard. This uses an Allegro structure. We'll look at structures in more depth in the next module, but for the time being, you just need to know that they're basically variables that can hold multiple types of data. So we create a keystate variable of the type Allegro keyboard state, and we provide it with al_getKeyboardState. This function, unsurprisingly, initializes it with basically a map of the keyboard and information as to which keys are pressed at that moment. Then we use al_keyDown to search for the status of a particular key using this map. If the key is being pressed, then the function returns true. As parameters, this function takes what are essentially special Allegro key codes. Using this in an if statement allows us to have code that executes on a button press. Both of these functions require an ampersand before our variables, just like scanf. We'll talk more about this in a later module as well. While a simple program may start by creating some data and presenting it, dynamic and interactive applications like a game go through a constant process of updating data and showing content on the screen. A typical video is 24 or 30 frames per second, meaning that the screen will be refreshed that many times in 1 second. Each frame is a single image that shows the content, a collection of objects in one state. Video games and other applications can have a higher frame rate, and indeed they should. Any interactive application performs better with a higher frame rate because the application will feel more responsive to the user. Not much feels worse than a program pausing to consider what the user has done before reacting to it. As we mentioned before, It's common for graphical applications to use secondary buffers to generate the frame and store it until it's complete before sending it off to the graphics card. A typical dynamic program will have three main parts. Initialization, which occurs at the start of the program, creates all the persistent data that will be used throughout the program, such as objects. After this step, the program uses a loop for creating frames. In each iteration, the two other parts will execute. Update occurs first, which is where the program responds to various inputs and events and changes its data, such as the location of an object. Next, the draw or render phase executes. This is where the objects are drawn and then displayed on the screen. Sometimes the loop will be artificially extended to ensure that frames aren't sent early. This is called frame pacing and basically means making sure that the frame rate doesn't vary. Variable frame rate can be distracting or confusing to a user, so it's best to be avoided. It's worth noting that the update part of our program corresponds to the input and process phases of our earlier programs, and the draw part corresponds to the output. Also, all the data used throughout the program will be created and initialized only once, before the main loop at the beginning of the program. Changing variables will happen in the update part. Before draw gets going, the buffer gets cleared. This is to prevent information from a previous frame interfering with this next one. At the end of draw, the display gets flipped as usual. You should bear in mind that things drawn first will effectively be displayed behind things drawn later. Drawing a rectangle in a particular region of the screen is done with a double or nested loop and using the putPixel function as shown in Allegro sample 1. To simplify the process of drawing the rectangle, we can create a function for it. This function has the following parameters: x and y coordinates, width and height, and also red, green, and blue color channels. The loops scan through each pixel on the screen within that region, and putPixel sets the color of the pixel at that location to be the color specified. This version of the code is subtly different to the one in the last tutorial. If you recall, that one worked by drawing a rectangle between two individual points, rather than one point and a certain distance away from it. Have a look at the two and compare them. Well, that wraps up this module. We'll see you in the next one.